Okay, let us continue the discussion. In the previous video, before the break, we talked about the basic setting of decision. And now we talk about a basic point estimation decision with only one parameter. That means the lambda is a scalar. Okay. And in this video, I just want to show one thing, very simple. I want to show that the decision delta is in fact equal to the expected value of lambda conditional on x. Okay. And so it is the regression of lambda on x. And in this video, I will show two proof. Um, One proof use simple calculus and another one use some algebraic manipulation. Okay, let me talk about the first proof. We call that the decision is minimizing base width. Here, I rewrite the base width here. Remember, the base width is the expected value of the width function, and width function is the expected value of the loss function. So the base width is this double integral over lambda and x. And in particular, the loss function here is the quadratic distance between the decision and the parameter. Okay, then let me change the order of two integration because we want to derive what is the decision delta for each value of x. Now I change the order of integration, and then now the inner integral is the expected value of the loss function over the lambda. That means it is the conditional expectation given x. And I highlight my algebraic manipulation in red color. So essentially what I did here is I multiply and divide by the marginal distribution f capital G, so that I have the posterior density here. Okay, remember the posterior density is the density of lambda given x, right? Because here I want to calculate the expected value of the loss function given x, right? Then to minimize the base width essentially means minimizing the inner integral for any given value of x. Okay, so now we consider the inner integral and take derivative, and then we set the derivative equal to 0. Very simple. Okay, just like here, we differentiate the integral with respect to delta and then set equal to 0. It is very straightforward to verify that the delta is equal to this integral. But what is this integral? It is exactly what we need. It is the expected value of lambda conditional on x. Remember, this is the posterior density. Okay, so this is the first proof, a very simple proof. Now I derive another proof of our conclusion. Here, we denote the optimal decision by delta G. By definition, W delta G will be smaller than the base width for any other decision, right? So that's why we have this inequality. And we will make use of this inequality to derive the conclusion that we want, okay? Now, once again, I write down the definition of base width here, the expected value of loss function over x and delta. And the algebraic manipulation that I do here is just minus and plus delta G, okay, because I want to split it into three different terms. And then I break the integral, I break the parentheses. That means I calculate these quadratic terms. Then this quadratic term will be equal to these three terms here. And the important thing to notice is that the second term, if I take integration over the second term, it is exactly the minimized base width with the optimal decision. Okay, so I write here in red color the second term. So I can take the second term out. That means the integration of the second term, I can take it out, and then I write here, it is exactly the minimized value of W. And then the other two terms are written here, the quadratic terms and the cross product term. The quadratic term and the cross product term. And the second quadratic term here, trivially, we know that it is non-negative, right? It equal to 0 when delta is equal to the optimal decision, and larger than 0 when they are not equal to each other. The important thing is the last integral. The last integral equal to 0, then the inequality written here will hold. Okay, so what is this inequality? Let me repeat once again. This is the inequality by definition should hold for optimal delta G. It should be the smallest. And if this integral equal to 0, then this inequality should hold. Okay, then let me use this necessary condition. I rewrite the third integral. That means the last integral here. The last integral here. We want it to be equal to 0, right? We want it to be equal to 0. And then let me do some manipulation. The manipulation that I do here is very simple. I just take the integration sign inside and I rewrite it in red color here. I just want to highlight that all the terms with lambda are here. Okay. And in order for this whole integral to be equal to 0, the inner integral in red color has to be 0, right? So we can make use of this condition to derive our conclusion. The last line is some more algebraic manipulation. I try to rewrite things in terms of posterior density. Essentially, I multiply and divide by the marginal density. So the ratio here is exactly the posterior density. And then this integral need to be 0, but what is it? But what it is? If you remember in the first proof, it is exactly the first order condition that we have in the first proof. And this condition will imply that the delta G for any given value of x will be equal to the expected value of lambda conditional on x. That means the posterior mean of lambda. Okay, we get the same conclusion. So here are the two proofs. And lastly, this video ends by these two remarks. And as we show, the point estimate decision is a regression of lambda on x. And also, the second remark is in the second proof, there is a byproduct. We get a formula of calculating the base width for any delta. Okay, so this is a byproduct from the second proof.